Hello, everyone, and welcome. Today, we are going to be talking a little bit about math, and mostly about programming, obviously, because that's what I like to do. Basically, the reason I came up with this video is because there are two YouTube sites that I follow, two YouTube channels that I follow. One, Michael Penn, is a math professor and puts out amazing videos about math and teaching about math and algorithms and things like that, and quantitative reasoning, which I really enjoy. And then I'm also a bit of a chess nerd, as you've probably seen in the past. I've done a few chess videos, and one of the and recently, Michael Penn and Nelson Lopez, who runs the Chess Vibes channel, which I also follow, got together, and one of them gave Professor Penn gave Nelson a math lesson, and Nelson gave Professor Penn a chess lesson, and this is playing off of the math lesson. Basically, the question that was posed to Nelson was, can we find the last digit of this? And I want to actually do that, and I'm going to do that in Python. I'm going to build that in Python. It is interesting to note when when Professor Penn was talking about this, when he first posited the question, he said computers these days wouldn't be able to calculate this number, and I immediately thought that doesn't seem like a very large number. He obviously knows what he's talking about, and he did follow up with, if they could, we could come up with a number that was big enough that they couldn't calculate. Where you couldn't just calculate the full number and then find the last digit. And that I accept. I did double check this. I was very curious, and you can, in fact, simply do this, right? So this is 433 to the exponent of 1297. And if I run this, we do in fact get the correct answer here. So let's just run that. So there you go. The last digit is 3. So we solved that problem. So what I actually want to do though is create a function in Python that will accept a number and an exponent, and it will calculate what the correct answer is, what that final digit is going to be, and it'll do this in Python. Some interesting things here. I mean, the explanation, I would take a look at the explanation in math. I think I have a simpler way of going about doing this, and that's probably because I'm using Python, because I'm thinking of this in terms of of programming rather than from a mathematical standpoint. So I do encourage you to watch the video. This is not in any way intended to take away from what can be learned there. I just want to show how I would do this in Python. If I were asked the same question, what would I actually do? At a very simple level, right, we know that this is in fact doable, right? We know that this, we'll just convert this to a string, and then we print the final digit, right? And now if I just do that, we get a 3, right? Which is expected. That was the last digit. And if we add another 0, let's just add another 2 zeros. It takes a little bit longer to calculate, but we do in fact get the answer back. And if I keep adding zeros, eventually it'll just take so long that basically my computer can't calculate it. So let's find a way where we can actually make this happen. Now, what I would propose is that we sort of shorten this, and this is kind of the route that the professor took in the video. Since we're only interested in the last digit here, we actually don't care about anything that comes before the last digit. So if I have, for example, the 3 times 3, right, and this is a regular times table, and we get back 9, right? 3 times 3 is 9. Now, if I have 13 here, so 3 times 13, we take the 3 and the 3, and we get back 9. And then we add a 0 here, and this digit is going to be that 3 times 1. So we get back 39. Now, that's obviously very easy to do in our heads, but you can very quickly see that this last digit multiplied by whatever other digit we have here is actually what's important. right? The final digit, if we're just taking the exponent, the final digit is the only thing that really matters. So this 433, the 43 in there doesn't actually make a difference. And let me demonstrate that, right? If I take 433 and I've got this exponent, so that's 1. If I remove the 4, that's a 1. If I change that 4 to a 3, that's a 1. If I change, let's just do to the 12th, and let's do all those, that's a 1. If I do a whole bunch of gobbledygook, that's a 1, okay? Because the 3 didn't change. As soon as I change that, now it's going to be a 6. And if I change any of these different numbers, it's going to end up being the same exact result. With that too. It's not the rest of these numbers that actually matter. It is only the last number, because that is what is in fact going to be multiplied at the very end. So I think that's a pretty simple explanation of basically how to approach this, how to approach thinking about this problem. But obviously this is not really the number that is a problem. This can be computed relatively quickly. So let's actually throw that back in there. And we know that that's a 3, okay? So next step, what are we actually going to do here? So I'm planning on taking the approach of stripping this out, and then I'll have a while loop for the exponent, and we'll just keep, so stripping out the first numbers, any numbers except for that last one. And we're going to have a while loop, and we're just going to keep multiplying it together, and then we'll use the while loop. Now, this is going to be like a pretty, it's not going to be a constant processing time. It's going to be pretty, as the number gets bigger, it's going to take longer and longer and longer to compute. And so we'll approach a way, we'll take a look at how can we actually cut that down so that it will have at maximum 10 iterations, probably 9 iterations really. So at maximum, it'll end up with 9 iterations, and then it'll be able to just compute the number based off of these results. So what we're going to do here is we're going to first create that while loop, and we'll just talk through how this can actually be done. So let's say here, so we've got our first number. Let's say last num is going to be string. We're actually going to do int string num -1. So that's going to be the last digit of the number. And we're going to say while exponent, right? For x in range exponent, we are saying last num, and this doesn't actually matter. This here doesn't actually matter. So the last num is going to be multiplied by last num. Okay, so it's going to be multiplied by itself. And then we're going to say last num equals this whole thing. So we're actually, let's say here first init is going to be this, right? And then we're going to say the last num times init. That'll be slightly cleaner. Right, and then we'll times equals init. Now we need to define last num, which in this case is just going to be init. Okay. Now, why are we getting errors? Unindent. What's wrong with the indentation? Oh, we're using tabs instead of spaces. All right. Indentations to spaces. Thank you, Sublime. Okay, so then we'll just print the, we've got to say last num equals int string num and the last character of that string. So we're basically gonna end up dividing it by 10, right? I could actually just say, I'm just gonna do the modulo equals modulo last num modulo 10, right? This would work in this case. And let me actually do that. It is num modulo shift 5 modulo 10. Okay, so basically that last number. So we're going to divide it by 10 each time and get the remainder. And then we're just going to say what the last num is. So theoretically, if we do this, we should get back 3. Now, clearly I did something wrong here. So we multiply last num by init. So let's say here, range exponent. That's the number of times that it should get multiplied. Should be exponent minus 1. Yeah. So I did my counting incorrectly. So this, in fact, should be from 1 to exponent, right? It should start actually at 1 and stop at exponent, because we don't have a to the 0th in this case, because that would just be 1. Okay. Anyways, so here we go. So this gives back the correct number. Now, as we add in more zeros here, this is just going to take longer and longer to compute. As you can see, it's still pretty fast. I had to add in a couple zeros here in order to make it really take forever. We're going to wait for that to compute, and I'm just going to start talking about how we could actually improve this process to be even faster. Because, frankly, this iteration, right, the larger this number gets, the longer it's going to take to go through this entire iteration. Now, the fun thing about these numbers, and especially the last numbers, is if we have something like 3, and then we multiply by 3, we get 9. And then we get multiplied by 3 again, we're going to get 7. This is actually 27, right? 9 times 3 is 27, but we only care about the last digit. And then we multiply that by 3 again, we get 1, right? We get 21. That's 7 times 3 is 21. We don't care about the 2. And then we get 3 again if we multiply 1 by 3. So we actually have a total of 1, 2, 3, 4 different numbers that are going to show up here, and this goes through on a loop. So we could in fact calculate what this number is by just going through essentially 4 loops, figuring out which divisor matches each of these numbers. This is going to be 1, this is going to be 2, this is going to be 3, this is going to be 4, and then we will calculate what the result is based off of the modulus 4 in this case. So 12. I'm going to cancel this. So 1297 modulus 4 should end up giving us a 1, right? If I'm doing my math right. 16, yeah, so this goes away. That doesn't mean anything. This ends up being an 8, which divides into 4 2 times, and then we end up with 16, which divides into 4, and we end up with a 1, which gives us the first place here. So this ends up having a remainder of 1 when we modulus 4. Okay, anyways. Okay, let me get rid of this, right? And now we're going to create a slightly different loop. And what we're going to say is for I in range, and we're going to do range 10 here. And the very first... and so what we need to do is we need to keep track of the divisors. Or the last nums here. So we're going to have the last numbers here. And we're going to say for I in range 10, we're going to pull in the number, and we're basically going to do this entire process, but only for that range of 10. So we've got our initial numbers, and this is our last nums. This is going to be init, right? Last nums is going to have init in it. That's to start with. Then we're going to take, instead of this for loop, we're going to use this for loop. We've got our last num. We use the modulo on that, and then we say last nums append last num. Now, you'll notice, right, let's actually say, we'll just print the last nums here. So these are the very last characters in each of these numbers. So let's just print that out. So you can see here, there's the 3, 9, 7, 1, 3, 9, 7, 1, and this would go off into infinity, right? This would actually go off as many times as we have this iteration here. So the key here is actually going to be, oh, we'll just take the modulus, right? We've been taking the modulus of 10. Now we just need to take the modulus of this number for whatever the length of unique characters is for this last nums piece. Now we're going to add a break here. So if last num in last nums, then we're going to break. Otherwise, we're going to append. Okay, so there we go. So now we just have 4 values. So now we know what that divisor should be, and we can say exponent. So we'll say remainder is exponent. Just scroll up here just a little bit. Is going to be the exponent. Modulus. Fat finger. Modulus the length of last num. Okay. And that's going to give us the remainder. And theoretically, if we return the value, we should be able to just return, or let's say print for right now, last nums, and this is going to be the remainder, and this is going to be minus 1. So this would be 1, this would be 2, this would be 3, this would be 4, and then it would repeat over at 5, 6, 7, 8, right? So in this case, we want the remainder minus 1. So let's do that. Oh, int has no length. Of course it doesn't have a length. Last nums. Whoop. Because there we go. Okay. So the response here is 1. That we should get back 1. And in fact, if we well, let's, there we go. That is 1. Let's actually double check this by printing 433 to the, I'm just going to copy that. We're just going to print that. Oh, that's taking a while. Of course it's taking a while. Okay, let's cancel that. Let's take off a few zeros. There we go. So there's the 1. It actually calculated. Let's check the original one. There's the 3. We know that we should get back a 3. That's a really long number. And it's getting back a 1. No. Why is it giving back a 1? Oh boy. Oh boy. Oh, because they're 2 entirely different numbers, of course. Okay, that's a 3. There's a 3. Okay, so it was in fact correct. All right, so this function should return last nums remainder minus 1. So what we're actually going to do here is we're going to say we're going to create another function, and this will really only work for very small numbers, right? This will work for pretty big numbers, pretty big exponents. The number itself doesn't really matter because we're just going to look at the last digit. The exponent is going to be could be extremely large because ultimately we're just going to be dividing it, modulusing it by the length of the last numbers. Now, if you're like me and you're curious about what the largest list size is ever going to be, that is in fact going to be a 9. It goes 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. And so the 9, if your number ends in a 9, that's going to be the longest last nums. I think it'll actually be 10, not 9, because it has every single number. There you go. So if you have any questions on this, let me know. Post any comments below the video. I will also include a link to the video that I was referencing that has the math description. It includes things like Euler's theorem, Euler's numbers. Very interesting, but from a programming perspective, I thought that this was actually a little bit easier to understand. So I wanted to do this, and also just because it's fun, and I like to put stuff like this together. So there you go. Like I said, if you have any questions, comments, throw them below the video. If you like this, let me know in the comments. If you didn't like this, also let me know in the comments. Like, I don't care. Feel free to let me know what you like, what you didn't like, because I'll read that and take that into account. If if you're crazy about this video, maybe subscribe. Who knows? So thank you very much. Have a good day. See you in the next video.